A sudden, silent scream echoes from the void of space. For decades, we have pictured black holes as the universe's ultimate vacuum cleaners, silent monsters lurking in the dark. But what if they are not silent at all? What if they are cosmic broadcast towers, sending out bizarre and unexplained signals that defy the very laws of physics as we know them? By the end of this journey, you will have explored 25 of the most perplexing cosmic enigmas ever detected, each one a story where reality seems to bend. We will uncover signals that repeat with chaotic rhythm, ghostly particles traced to violent jets, and whispers from mergers that shook space-time itself. How many secrets can a singularity truly hold? That silent scream began with a single, electrifying burst of data. In August of 1977, an astronomer named Jerry Amon was reviewing printouts from Ohio State University's Big Ear radio telescope, a machine quietly listening to the cosmos. His eyes scanned the columns of letters and numbers, a routine check for anything unusual. Then he saw it. A sequence so powerful, so perfectly aligned with the expected signature of an artificial signal from beyond our solar system, that he circled it on the paper and wrote one word in the margin. Wow. The wow signal, as it became known, was a 72-second roar of intense radio waves, a narrowband beacon that appeared and then vanished forever. It came from the direction of the constellation Sagittarius, a patch of sky with no known stars. For decades, the leading theory was that it was a message, a deliberate broadcast from an advanced civilization. But if that were true, why was it never repeated? Why send a cosmic hello just once? This is where the shadow of a black hole enters the story. Imagine a signal, perhaps a faint, routine transmission from a distant galaxy, traveling for millions of years. Its path is mostly empty until it passes near a massive, invisible object. The black hole's immense gravity acts not as a destroyer but as a lens. It warps the fabric of space around it, bending the path of light and radio waves. Just as a magnifying glass can focus the sun's rays into a burning point, a black hole could focus a distant, faint signal into an intense, brilliant flash aimed directly at Earth. For those 72 seconds, our planet was in the precise focal point of this cosmic lens. We heard a whisper from across the universe, amplified to a shout. Then, as the alignment shifted, the signal faded back into the background noise, never to be heard again. This hypothesis transforms the wow signal from a potential message into a cosmic accident, a fleeting mirage created by the universe's most extreme physics. It means we might not have been the intended recipient at all. We simply happened to be in the right place at the right time to catch a ghostly echo focused by a dark, wandering star. The wow signal was a solitary whisper, a single note played in the cosmic dark. But what if the universe has an entire orchestra of these strange transmissions? In 2007, a team of astronomers sifting through old data from the Parkes Radio Telescope in Australia found something that would redefine the search for cosmic anomalies. It was a burst of radio waves so powerful, so concentrated, it released more energy in a single millisecond than our sun does in 80 years. They called it a fast radio burst, and it was not alone. These FRBs are the universe's most energetic flashbulbs, flickering on for just 1,000th of a second from billions of light years away. For years, their origin was a complete mystery. Could they be the dying cries of stars being shredded by black holes, or perhaps the catastrophic collisions of ultra-dense neutron stars? The leading suspect today is a type of stellar corpse called a magnetar. Imagine a neutron star, the collapsed core of a giant star spinning rapidly. Now crush its already insane magnetic field down to a scale you can comprehend. A magnetar's magnetic field is so strong it could strip the information from every credit card on Earth from halfway across the galaxy. Theorists suggest that starquakes on the surface of these magnetars, or sudden rearrangements of their magnetic fields, could snap like cosmic whips, launching those incredible bursts of radio energy across the universe. This theory gained tremendous support in April of 2020, when a magnetar named SGR 1935+2154, located right in our own Milky Way, erupted. It didn't just produce X-rays, which magnetars are known for. For the first time ever, we caught one emitting a fast radio burst, a faint but undeniable twin to the colossal extragalactic signals. It was a smoking gun linking a specific object to this phenomenal phenomenon, yet the mystery only deepens from there. If magnetars are the source, why do their signals behave so differently? Take FRB 121102, the first repeater ever discovered. It sits in a dwarf galaxy 3 billion light-years away, and it fires off bursts in chaotic, unpredictable clusters. Sometimes it is silent for months, then erupts dozens of times in a single day. There is no rhythm, no pattern, just a temperamental cosmic lighthouse. Meanwhile, the vast majority of FRBs are one-off events. They flash once with incredible power and are never heard from again. This presents a fundamental puzzle. Are the repeating bursts and the one-off bursts coming from the same type of object, but in different stages of its life? Or are we looking at two completely different cosmic engines? Perhaps a one-off burst is the final catastrophic death scream of a magnetar, while a repeater is a younger, more active object throwing tantrums as it settles down. The existence of these signals tells us that the environments around black holes and neutron stars are far more volatile and electrically charged than we ever imagined. They are not just silent graves, but factories for the universe's most extreme and unexplained transmissions. The chaotic rhythm of FRB 121102 defies any cosmic clock. This was not just another flash in the dark, it was the first signal of its kind to ever speak twice. After its initial detection, astronomers kept listening, and to their astonishment, the bursts kept coming. They arrive in unpredictable clusters, a frenzied staccato of cosmic noise. For weeks it might fall silent, a dormant mystery, then suddenly erupt with dozens of bursts in a single day. This behavior alone shattered the idea that all fast radio bursts were one-time cataclysms. It pointed to a source that could survive its own outbursts, a cosmic engine that could fire again and again. But the true revelation came when scientists finally pinpointed its home. It resides not in a grand spiral galaxy like our Milky Way, but in a tiny, unassuming dwarf galaxy 3 billion light-years away. This galaxy is a cosmic toddler, rich with the raw materials for star formation, and crucially, it harbors an environment of staggering magnetic fury. The region surrounding the burst source is magnetized to an extreme degree, a maelstrom of twisted magnetic fields. This discovery fueled the leading theory that we are listening to a young, hyperactive magnetar. Picture a stellar infant, a neutron star only a few thousand years old, born from the violent collapse of a massive star. Its magnetic field is still settling, still unstable. Like a child throwing a tantrum, this young magnetar could experience frequent starquakes or magnetic reconnections, each event snapping like a whip and launching those intense radio bursts across the universe. Its chaotic pattern reflects the turbulent adolescence of a supremely powerful object. Yet not all scientists are convinced. An alternative, equally fascinating idea suggests we might be witnessing a cosmic dance between two extreme objects. Imagine a pulsar, a rapidly spinning neutron star that emits a steady lighthouse-like beam of radiation, locked in a tight orbit around a black hole. As the pulsar travels along its elliptical path, it periodically plunges through the black hole's intense gravitational field and the dense cloud of magnetized plasma that surrounds it. This environment could act as a lens or a shutter, only allowing the pulsar's beam to reach us at specific points in its orbit, creating the illusion of chaotic, repeating bursts. The debate is ongoing, a testament to how one strange signal can split a scientific community. Is it a solitary, youthful titan throwing magnetic fits, or a deadly orbital ballet where a pulsar's cry is periodically amplified and silenced by a dark companion? FRB 121102 holds the answer, but for now, it communicates only in cryptic, repeating bursts. The idea of a pulsar's beam being shuttered by a black hole is a dance of immense scale, but our own galactic center holds evidence of a far more catastrophic performance. Rising from the heart of the Milky Way, stretching for 25,000 light-years above and below the galactic plane, are two colossal orbs of energy known as the Fermi Bubbles. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these are not fleeting signals but a permanent, simmering monument to some ancient violence. Imagine two vast, symmetrical balloons, each one glowing with high-energy gamma rays, dwarfing our entire galaxy's visible disk. They are a ghostly echo of an event so powerful it punched through the dense gas of the galactic core and has been fading for millions of years. The most logical architect for such a structure is Sagittarius, a star, the supermassive black hole sitting at the very center of this chaos. While it is quiet today, the Fermi Bubbles are proof it was not always so. The leading theory is that Sagittarius, a star, experienced a period of intense activity, perhaps feasting on a massive cloud of gas or shredding an entire star in a tidal disruption event. This feast would have unleashed a titanic amount of energy, not in a single direction like a jet, but in two opposing outflows that blew outward, inflating these gigantic bubbles like cosmic bellows. But the sheer scale and perfect symmetry of the bubbles present a profound puzzle. What kind of eruption could be so perfectly balanced, creating two near-identical structures that have persisted for millions of years without collapsing or distorting? A simple jet of material would likely be wobbly or one-sided. This suggests an event of astonishing stability and power, a sustained burp from the black hole that lasted for tens of thousands of years. It forces us to reconsider the life cycle of a supermassive black hole. They are not just sleeping giants, they are cyclical engines capable of entering violent, eruptive phases that can reshape their entire host galaxy, leaving behind these immense, glowing scars as the only testimony to their past fury. While the Fermi Bubbles represent a black hole's eruption over eons, some signals capture a single, violent feast in exquisite, real-time detail. In November of 2014, an automated sky survey called Assassin spotted a sudden flare in a galaxy 290 million light-years away. This was not a supernova, the death of a star from within. This was something far more visceral. A star wandering too close to a supermassive black hole had been caught in its gravitational grip. The black hole's tidal forces, the difference in pull between the star's near side and far side, stretched and shredded it into a long, thin stream of gas in a process called a tidal disruption event. For months, telescopes watched the aftermath as this stellar spaghetti swirled into a glowing, chaotic disk around the black hole's event horizon, a brilliant beacon of destruction. But the true signal, the real discovery, was hidden within the X-rays. As the all-sky automated survey for supernova monitored the visible light flare, NAS, a Swift and Chandra X-ray observatory, trained their instruments on the event named Assassin 14 Li. They expected to see a steady, fading glow as the debris was consumed. Instead, they saw a heartbeat. The X-ray emissions began to flicker, to pulse with a regular rhythm. Every 131 seconds, like clockwork, the signal would brighten and fade. Scientists realized they were not just watching a glow, they were listening to echoes. These precise fluctuations were X-ray light bouncing off the innermost regions of the speeding debris stream as it whipped around the black hole. For the first time ever, astronomers could use these echoes like a medical scan, mapping the structure and size of the debris disk in real time as it formed. It was as if the black hole itself was illuminating its own dinner plate. Yet the deepest mystery emerged from the source of those X-rays themselves, a region of searingly hot plasma just outside the event horizon called the corona. As the stellar debris rained down, the corona did something astonishing. It grew 50 times brighter and, according to the data, appeared to contract, to move dramatically closer to the black hole's deadly point of no return. Why would a feeding frenzy cause the corona to shrink and intensify? One theory suggests the incoming flood of stellar gas compressed the magnetic fields that contain the corona, squeezing it into a smaller, hotter, and more energetic state. Another, more radical idea proposes we witnessed a literal shift in reality, where the immense energy of the infalling debris actually caused the black hole's event horizon to swell outward temporarily, making the corona appear to move closer relative to this new boundary. Assassin 14 Lie transformed a catastrophic death into a precise diagnostic tool, giving us a front-row seat to the dynamic and violent physics that occur in the final moments before matter vanishes forever. The rhythmic echoes of a star's death showed us how a black hole can illuminate its own feast. But in our own galaxy, another object has been broadcasting its own steady, living heartbeat for decades. GRS 1915 plus 105 is a microquasar, a binary system where a stellar mass black hole, about 14 times the mass of our Sun, is locked in a deadly dance with a companion star. It is slowly devouring its partner, pulling gas from it into a swirling, glowing disk of superheated plasma called an accretion disk. Most black holes with a steady food supply flicker and flare with some irregularity. But GRS 1915 plus 105 is different. It has a pulse. Every 20 to 40 minutes, like a colossal cosmic metronome, it erupts in a powerful burst of X-rays before dimming again. This quasi-periodic oscillation is so stable and so distinctive, astronomers refer to it as the black hole's heartbeat. The leading explanation for this eerie rhythm lies in the physics of the inner accretion disk, the final furious whirlpool of matter just outside the event horizon. Imagine a bathtub with a slow, steady trickle from the faucet, but the drain is partially clogged. Water begins to pool. The pressure builds and builds until suddenly the clog gives way and a large volume of water rushes down the drain all at once. Then the cycle begins again. Scientists believe this is what happens around this particular black hole. Material from the companion star streams into the outer disk and spirals inward. But near the very edge of the black hole's grasp, the flow seems to hit a bottleneck. The intense heat and magnetic pressure cause the inner disk to become unstable. Gas accumulates, heats to millions of degrees, and becomes trapped. This goes on until a critical threshold is crossed. The built-up material then rapidly overcomes the pressure barrier and plunges into the black hole in a sudden, violent rush, releasing that characteristic burst of X-rays we detect as a heartbeat. Then the inner disk is emptied, the process resets, and the cycle begins anew. This raises a profound question. Why does this one black hole, among the many we have observed, exhibit such a clean, clockwork signal? The answer likely lies in a perfect and fragile balance. The rate at which material is being fed from the companion star must be in a very specific, narrow range. Too little, and the inner disk cannot accumulate enough material to trigger a regular outburst. Too much, and the flow becomes a continuous, chaotic torrent, drowning out any rhythmic signal. GRS 1915 plus 105 appears to be in this cosmic Goldilocks zone, with a feeding rate that is just right to sustain this incredible instability cycle. It is a unique laboratory, showing us that the process of accretion is not always smooth or random. Under precise conditions, it can become a predictable, oscillating engine, allowing us to study the detailed physics of how matter behaves in its final moments before crossing the point of no return. This steady pulse is not a sign of life, but a signature of a perfectly tuned machine of destruction. That steady heartbeat is a whisper compared to the cosmic shout of a new and baffling phenomenon. In 2019, astronomers using the ASCAP radio telescope in Australia were mapping the sky when they stumbled upon something that should not exist. They called them odd radio circles, or ORCs. These are not faint smudges, but enormous, perfectly circular rings of radio emission, so vast they could swallow our entire Milky Way galaxy many times over. The strangest part, they are completely invisible in optical, infrared, or X-ray light. They exist only as ghosts in the radio spectrum, with a single, ordinary-looking galaxy sitting quietly at the very center of each one. They are not the remains of a supernova. Those are far too small and chaotic. They are not galactic winds, which typically have a different shape. These are pristine, colossal halos, and they have no clear explanation. The most compelling theory points directly to the supermassive black hole at the heart of each central galaxy. Imagine hundreds of millions of years ago, that black hole experienced a cataclysmic event. Perhaps it merged with another supermassive black hole, a collision that sent a gargantuan shockwave of energy blasting outward in all directions. Or maybe it entered a brief but incredibly violent feeding phase, a quasar eruption that has long since faded. This titanic burst would have created a spherical tsunami of charged particles and magnetic fields, expanding at nearly the speed of light. Over countless millennia, this shockwave traveled outward, sweeping up and energizing the thin gas that exists between galaxies. Today, we see the glowing aftermath, the immense radio-bright edge of that ancient wave, frozen in time as a perfect circle. It is a fossil of a black hole's past fury, a relic so large it took light ages to cross it, and we are only now seeing the echo of a moment that ended before dinosaurs walked the Earth. Our galaxy's ghostly radio circles are echoes from a distant past, but in 2017, a single ghost particle delivered a message from the present. Deep under the Antarctic ice at the South Pole lies a detector unlike any other. It is not a telescope, but a grid of over 5,000 light sensors buried more than a mile down in the pure, dark ice. This is the Ice Cube Neutrino Observatory, and its purpose is to hunt for the universe's most elusive travelers, neutrinos. These are ghost particles with almost no mass and no electric charge, born in the hearts of stars and in the most violent cosmic events. They pass through planets and people as if they were not even there. On September 22, 2017, Ice Cube captured one that was different. It was a single, high-energy neutrino carrying an astonishing 300 tera-electron-volts of energy. It slammed into the Antarctic ice, and in the flash of blue Cherenkov radiation it produced, a new era of astronomy began. For the first time ever, scientists could trace the path of this cosmic ghost back to its source. They sent out an alert, and telescopes around the world and in space swiveled to look. Their collective gaze pinpointed a galaxy 4 billion light-years away, known as TXS 0506 plus 056. At its core was not just any supermassive black hole, but a blazar. A blazar is a monster with its particle cannon aimed directly at Earth. As the black hole feeds, it launches twin jets of plasma at nearly the speed of light. When one of those jets is pointed right at us, we see it as an intensely bright beacon across the electromagnetic spectrum, from radio waves to gamma rays. The alignment was perfect. This single neutrino had come screaming out of that jet. The significance of this detection cannot be overstated. It was the first time a high-energy neutrino was ever linked to a specific object in the sky. This proved that the chaotic, magnetized jets of supermassive black holes are among the universe's most powerful particle accelerators, far more potent than anything we could ever build on Earth. But how does a black hole's jet accomplish this? The process is thought to involve shock waves within the jet itself. As the jet plows through the sparse intergalactic medium, or as faster material slams into slower material within the flow, it creates immense shock fronts. Charged particles like protons can get caught bouncing back and forth across these magnetic shock waves. gaining a tremendous boost in energy with each pass. Eventually, these ultra-high-energy protons can collide with photons or other particles within the jet. That collision is what creates the neutrino, a byproduct that carries a portion of that insane energy away. Because neutrinos barely interact with anything, they fly straight out of the jet, giving us a clean, direct signal from the engine's core, unaltered by magnetic fields or intervening dust. This event marked the true dawn of multi-messenger astronomy. We are no longer limited to observing the universe only with light. Now we can combine the story told by photons with the ghostly testimony of neutrinos and the ripples in space-time from gravitational waves. Each messenger reveals a different part of the story. The gamma rays and X-rays show us the jet's overall fury and heat. The neutrino, however, is a smoking gun, direct evidence that protons are being accelerated to unimaginable energies in that environment. It is like listening to a storm. You can see the lightning, which is the light, but the neutrino is the crack of thunder, the sound wave that tells you about the power of the bolt itself. The detection from Blazar TXS 0506 plus 056 opened a new window into the most extreme engines in the cosmos, proving that black holes do not just consume light. They also forge the very building blocks of reality into ghostly messengers we are only just learning to read. The ghostly neutrino from the Blazar was a direct message from a jet aimed at Earth. But what happens when that cosmic cannon does not point at us and instead sweeps across the sky like a lighthouse beam? This brings us to one of the strangest periodic signals in the high-energy universe, emanating from a system called SS433. Located about 18,000 light-years away in the constellation Aquila, it is not a solitary black hole but a binary dance of death. A stellar mass black hole, roughly 10 times the mass of our Sun, is locked in a tight 13-day orbit with a massive companion star. The black hole is actively feeding, pulling a torrent of gas from its partner and forming a superheated accretion disk. From this disk, it launches two narrow, ultra-fast jets of plasma from its poles. These are not steady streams. They precess, meaning they wobble slowly in a cone-like pattern, much like a spinning top slowly tracing a circle as it loses speed. This wobble has a period of about 162 days. For most of that cycle, the jets are pointed away from our line of sight. But twice during each precession, one of those deadly particle beams sweeps directly across Earth. And when it does, we get a flash, not just in radio waves, but in the most energetic light of all, gamma rays. Satellites like NASA's a Fermi Gamma Ray Space Telescope have detected these periodic gamma ray pulses from SS433, a regular heartbeat of extreme energy timed perfectly with the jet's wobble. The mystery lies in the details of this process. How exactly does a jet of matter, traveling at over a quarter the speed of light, produce such intense gamma radiation simply by pointing in our direction? The leading theory involves shock waves and collisions. As the precessing jet plows through the surrounding interstellar medium, or even into material shed by the companion star, it creates immense shock fronts. Within these shocks, particles are accelerated to near light speeds. When these ultra-fast particles, like electrons, interact with light or magnetic fields in their path, they can boost that light up to gamma ray energies in a process called inverse Compton scattering. Essentially, the jet acts as a natural particle accelerator, and our vantage point gives us a periodic glimpse into its most intense shock zone. Modeling this intricate dance is a monumental challenge for astrophysicists. They must account for the complex hydrodynamics of the accretion flow, the physics of the jet launch mechanism itself, the precise geometry of the precession, and the chaotic environment of the binary system. It is a three-dimensional puzzle of extreme gravity, plasma physics, and orbital mechanics. Yet, this complexity is precisely what makes systems like SS433 so valuable. They are natural laboratories, allowing us to study the inner workings of relativistic jets in exquisite, time-resolved detail. By watching the periodic flashes change in brightness and energy, we can map the structure of the jet and the environment it travels through. Furthermore, the slow precession itself is a clue. It is likely driven by the subtle effects of general relativity, specifically frame dragging, where the spinning black hole twists the very fabric of space-time around it, tugging on the accretion disk and causing the entire jet system to wobble. By observing this precession, we are indirectly measuring the spin of the black hole and testing Einstein's theories in a regime of extreme gravity. SS433 transforms a distant cataclysm into a precise cosmic clock. Its periodic gamma-ray ticks revealing the hidden mechanics of how black holes channel their fury into the universe. The precise gamma-ray clock of SS433 reveals a black hole in its prime, actively feeding and shaping its surroundings. But this raises a deeper cosmological question. If black holes are such powerful engines, why is our local universe so quiet? Look at the supermassive black hole at the heart of our own Milky Way, Sagittarius, a star. It is a sleeping giant, a faint whisper compared to the roaring behemoths we see in the distant past. This is the silent quasar problem, one of the great puzzles in modern astrophysics, and the signal here is an absence, a profound and unexplained quiet. When we peer back to the universe's infancy, just a few 100 million years after the Big Bang, we find a sky filled with monsters. Quasars, the ultra-bright cores of galaxies powered by voraciously feeding supermassive black holes, shine with the light of 1 trillion stars. They were everywhere. The data is clear. The early universe was a banquet hall for black holes. Yet, in our modern cosmic neighborhood, such brilliance is exceedingly rare. Most giant black holes, including our own, are on a strict diet. They are dim, quiescent, and relatively peaceful. So what changed? What signal of cessation did the universe send to turn down the volume? The leading theory is a simple matter of supply and demand. The early universe was a much denser, more chaotic place, rich with cold gas and freshly formed galaxies constantly colliding and merging. These collisions funneled vast reservoirs of fuel directly into the waiting gravitational pits of supermassive black holes, igniting them into brilliant quasars. It was an era of cosmic excess. Today, the universe has expanded and calmed. Galaxies are more settled, their gas is hotter and more diffuse, and major mergers are less frequent. The fuel stations, in essence, have mostly closed. A black hole like Sagittarius, a star, simply does not have a steady, dense stream of gas to consume, so it flickers faintly on the scant material that occasionally drifts too close. But scarcity alone may not tell the whole story. Another compelling idea involves a powerful feedback mechanism, a case where the black hole's own activity shuts off its growth. Imagine a quasar switching on. As it feasts, it doesn't just emit light, it also drives tremendous winds and jets that blast outward at incredible speeds. These outflows can heat the surrounding galactic gas, pushing it away and preventing it from cooling and falling back in to feed the black hole further. It is a self-regulating cycle. The black hole's brilliant signal of consumption simultaneously broadcasts a command to stop. After a period of furious eating, it literally blows its own dinner off the table, forcing itself into a period of quiet starvation until enough gas can accumulate again. Our Milky Way may bear the scars of such past outbursts, with the immense Fermi Bubbles being a fossil of a last great meal that ended with a self-imposed shutdown. There is also the possibility of different accretion modes. In the early, gas-rich universe, black holes may have fed in a steady, efficient way, forming smooth, dense accretion disks that glow with intense heat, the classic quasar mode. In today's sparse environment, accretion might be chaotic and inefficient, like trying to feed from a sparse mist rather than a flowing river. Material falls in clumps and from random directions, never settling into a stable, bright disk. This inefficient, ad hoc feeding produces only faint flickers, not a sustained roar. The silence we observe, then, might be the sound of a black hole eating poorly. This cosmic quietude forces us to see black holes not as static monsters, but as beings with life cycles intimately tied to the evolution of their host galaxies. Their brilliant signals in the ancient sky were the cries of a violent, formative youth. The silence we hear today is the mature universe catching its breath, its most massive inhabitants settling into a long, dormant old age, their furious growth self-limited by the very power they once wielded. This cosmic quietude, however, may hide the faintest signal of all, a whisper predicted by theory but never once heard. Stephen Hawking proposed a revolutionary idea that black holes are not truly black. At the very edge of their event horizons, where gravity warps reality into a knot, quantum mechanics performs a subtle magic trick. Pairs of virtual particles, one with positive energy and one with negative, constantly flicker in and out of existence. Normally, they annihilate each other almost instantly, but right at the precipice of a black hole, gravity can intervene. One particle falls in while the other escapes. To an outside observer, it looks as if the black hole itself emitted a particle. This is Hawking radiation, a faint thermal glow that, over eons, causes a black hole to slowly lose mass and evaporate. It is the ultimate unexplained signal, not because it is loud, but because its silence is deafening. We have never detected it. The challenge is almost incomprehensible. For a typical stellar mass black hole, the Hawking radiation it emits has a temperature of just a few billionths of a degree above absolute zero. That is trillions of times colder than the cosmic microwave background, the afterglow of the Big Bang that fills all of space. Trying to spot this faint whisper against that blinding roar is like trying to hear a single snowflake land in the middle of a hurricane. So how could we ever hope to find it? One speculative idea looks to the universe's earliest moments. Theorists suggest that in the violent turbulence just after the Big Bang, knots of density may have collapsed directly into black holes no larger than a mountain range. These primordial black holes, if they exist, would be much smaller and hotter than their stellar cousins. A black hole with the mass of an asteroid would glow with a temperature of millions of degrees, emitting X-rays as it evaporates. Its final moments would be a brilliant flash, a gamma ray burst signaling its complete disappearance. Astronomers have searched for these telltale flashes, but so far the sky has offered none. Another frontier is not in space, but in the laboratory. Scientists have created analog black holes using sound waves in superfluid helium or light in optical fibers. In these setups, a point where the flow of the medium becomes faster than the speed of sound or light creates an artificial event horizon. Remarkably, experiments have detected analogs of Hawking radiation in these systems, a thermal glow of phonons or photons emerging from the artificial horizon. While these are not gravitational black holes, they strongly suggest Hawking's math describes a real, universal phenomenon. The hunt for the real cosmic signal continues, a quest for the softest breath from the darkest objects, a whisper that would confirm a profound truth, that even the universe's ultimate prisons are not eternal. The search for Hawking's whisper is a quest for the softest signal in the cosmos, but other unexplained transmissions are anything but gentle. They arrive not as light or heat, but as atomic shrapnel traveling at nearly the speed of light. These are cosmic rays, and among them exist particles with energies so absurdly high they defy a fundamental cosmic rule, the Greisen-Zatsepin-Kuzmin cutoff. Named for the three physicists who predicted it, the GZK cutoff is a universal speed limit for charged particles from distant galaxies. It states that any proton or atomic nucleus with an energy above a certain staggering threshold, about 5 × 10⁻¹9 electron volts, should not be able to reach us from beyond our local galactic neighborhood. The reason is the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Think of it as a faint, cold fog filling the universe. A proton traveling at such insane speeds from a distant galaxy would be like a race car blasting through a dense mist. it would constantly collide with the photons of this background radiation, losing a little energy with each impact. Over hundreds of millions of light years, these countless tiny collisions should bleed the proton dry, slowing it down below the cutoff energy long before it ever reaches Earth. The universe, it seemed, had built its own energy barrier. Then we started detecting them. Instruments like the Pierre Auger Observatory in Argentina, a vast array of detectors spread over an area the size of Rhode Island, have recorded over a dozen of these ultra-high-energy cosmic rays. They are rare, perhaps 1 particle per square kilometer per century, but they are real. Each one carries the kinetic energy of a professionally thrown baseball, all compressed into a single subatomic particle. Their existence is a direct violation of the expected law. So where do these rule breakers come from, and how do they cheat the cosmic fog? The prime suspects, once again, are the jets of supermassive black holes in active galaxies. The environment within these relativistic jets is a maelstrom of magnetic fields and shock waves, a natural particle accelerator of almost unimaginable scale. The process, called Fermi acceleration, sees charged particles trapped between magnetic mirrors in the jet, bouncing back and forth like pinballs, gaining a tremendous boost with each collision. Under perfect conditions, this mechanism could theoretically push particles to energies that surpass the GZK limit. But there is a catch. For a particle to reach us with such energy, it must not only be born in a phenomenal explosion, it must also have a very short journey. This points to a source relatively nearby, within a few 100 million light years, where the draining effect of the cosmic microwave background hasn't had enough time to fully slow the particle down. The mystery deepens because when astronomers trace the rough paths of these ultra-high-energy cosmic rays back into the sky, they do not always point to an obvious, brilliant active galaxy. The particles are deflected by the magnetic fields of intergalactic space, making precise pinpointing incredibly difficult. It is possible we are seeing particles born in the jets of black holes that are currently quiet or obscured from our view in other wavelengths. Or perhaps the acceleration mechanism is even more efficient than our models predict, launching particles with such initial ferocity that they can punch through the cosmic fog from greater distances than we thought possible. Each detection of a particle beyond the GZK cutoff is a message in a bottle, a fragment of a catastrophic event from a monstrous engine. It tells us that the jets from feeding black holes are not just beautiful streams of light. They are the universe's ultimate particle cannons, capable of firing atomic bullets with energies that challenge our understanding of physics itself. Ultra-high-energy cosmic rays are atomic bullets fired from distant cannons, but sometimes the universe sends a signal that flickers and fades not from distance, but from a deadly, intimate embrace. In the constellation Sagittarius, a cosmic predator stalks its prey. This is the Black Widow pulsar, a millisecond pulsar spinning hundreds of times per second, locked in a 9-hour orbit with a low-mass brown dwarf star. The pulsar's intense radiation and relentless particle wind are slowly but surely cooking its companion, stripping away its outer layers and evaporating it into a vast cloud of plasma. From our vantage point on Earth, this creates a bizarre and telling phenomenon. As the pulsar's lighthouse beam sweeps toward us, it must first pass through this shroud of stolen stellar material. The plasma acts like a dense, turbulent fog, scattering and absorbing the radio waves. For a portion of every orbit, when the brown dwarf is directly between us and the pulsar, the signal simply vanishes. It is not gone, it is being smothered by the very corpse of the star it is destroying. This cosmic eclipse by plasma is a perfect, terrifying analogy for a far greater mystery surrounding black holes. Imagine a similar scenario, but scaled up to apocalyptic proportions. Instead of a pulsar and a brown dwarf, picture a stellar mass black hole in a tight binary orbit with a regular star. As the black hole feeds, it does not just create a simple disk. it can generate a vast, swirling atmosphere of superheated plasma and gas and a accretion flow of unimaginable density. Now consider if there were a pulsar or another compact object also orbiting that black hole. Any signal from that object, be it radio pulses or even the systematic flicker of its X-rays, would have to travel through that violent, magnetized shroud to reach us. Just like the Black Widow's signal, it could be scattered, distorted, or completely absorbed. The black hole's feeding frenzy would create a permanent, chaotic eclipse, masking the presence of other objects in its immediate vicinity. This presents a monumental challenge for the newest field of astronomy, gravitational wave science. Our detectors like LIGO and Virgo listen for the ripples in space-time caused by massive objects spiraling together and merging. Their greatest triumphs have been hearing the collisions of black holes and neutron stars. But what if some of the signals we are listening for are being scrambled before they even leave their home system? A pair of neutron stars spiraling into a black hole would generate a unique gravitational wave signature. However, if that in-spiral is happening within a thick, turbulent accretion disk, the environment itself could alter the signal. The plasma could interact with the gravitational waves in subtle ways, or the immense drag of the gas could change the in-spiral rate, making the event look different in our data than our clean, vacuum-based models predict. We might be missing entire populations of mergers happening in these extreme environments, or misinterpreting the signals we do catch. The Black Widow shows us a clear, local example of how a dense plasma environment can erase a cosmic beacon. Around a feeding black hole, that effect could be 1 billion times more powerful, creating the ultimate cosmic static, behind which untold dramas of destruction could be unfolding in silence. The cosmic static around a feeding black hole could hide entire populations of silent mergers, but in September of 2019, our gravitational wave detectors heard a collision so loud it broke through every expectation. The signal, named GW190521, arrived as a brief, thunderous thud in the LIGO and Virgo observatories. Lasting less than 1/10 of a second, it was the merger of two colossal black holes, but their masses sent shockwaves through the astrophysics community. One was 66 times the mass of our Sun. The other was a staggering 85 solar masses. This was not just another merger, it was a direct challenge to our understanding of how stars live and die. The 85 solar mass black hole sits squarely in what theorists call the pair instability mass gap. According to our best models of stellar evolution, a dying star with a core between roughly 65 and 120 solar masses should not form a black hole at all. Such a star is destined for a far more spectacular fate. In its final moments, the core becomes so hot that light itself begins to create matter-antimatter pairs. This process saps the star's internal pressure, triggering a runaway collapse. The result is not a quiet fade into a black hole, but a titanic thermonuclear explosion so violent it completely obliterates the star, leaving nothing behind. No remnant, no black hole, just scattered stardust. So the existence of an 85 solar mass black hole is a profound paradox. How did an object that should have been impossible come to be? One thrilling possibility is that we are not looking at first-generation stars at all, but at a second-generation black hole, a descendant of earlier cosmic violence. Imagine two smaller black holes, each perhaps 40 or 50 solar masses, formed from stars that died in the acceptable mass range. Over eons, they could have found each other within a dense star cluster, spiraled together and merged. The product of that first merger would be a black hole of about 85 solar masses. Then, millions of years later, this newly forged monster found another partner and merged again, creating the final, even larger black hole we detected. This scenario paints a picture of a hierarchical universe where black holes in crowded environments can build up mass over multiple generations, like cosmic snowballs rolling through a stellar avalanche. The alternative explanation is even more exotic, reaching back to the very beginning of time. What if this black hole was never a star? Primordial black holes are hypothetical objects that could have formed in the first chaotic instance after the Big Bang from the direct collapse of dense knots of matter. They could theoretically exist in any mass range, neatly sidestepping the rules of stellar evolution entirely. A primordial black hole of 85 solar masses would be a relic from creation itself, a fossil wandering the cosmos since the dawn of time, only now revealing itself through a violent collision. JW 190521 forces us to confront the limits of our knowledge. Either our models of how massive stars die are incomplete, or the universe contains ancient, unseen populations of objects we are only beginning to glimpse. Each thud from the dark is rewriting the story of cosmic evolution. That 85 solar mass paradox challenges our models of stellar death, but the signals from a black hole's final frontier offer a more direct test of the laws of physics themselves. Deep within the flickering X-ray glow of a feeding black hole, astronomers have discovered a rhythmic pulse, a rapid, musical tremor in the data. These are quasi-periodic oscillations, or QPOS. They are not the steady heartbeat of a microquasar, but something far more intricate and fleeting, a shimmering vibration in the superheated gas just moments before it vanishes forever. Picture the accretion disk as a furious, glowing whirlpool. As matter spirals inward, it does not flow smoothly like water down a drain. It clumps, it shudders, it breaks into waves of hot plasma. These waves create patterns, oscillations that manifest as specific, repeating frequencies in the X-ray light we detect. Each frequency is like a note played by the black hole's gravity, a direct signal from the warped spacetime just outside the event horizon. The most precious of these signals are the high-frequency QPOS, rapid flickers that scientists believe originate in the innermost, most relativistic part of the disk. This is the last stable orbit, the final circular path matter can take before it must plunge irrevocably inward. The frequency of an oscillation here is dictated by the sheer strength of the black hole's gravity, which in turn depends on its mass and how fast it is spinning. In theory, if we can precisely decode this frequency, we could measure the black hole's spin and map the geometry of space in this extreme region, conducting a direct test of Einstein's general relativity under conditions no laboratory could ever recreate. Yet here lies the enduring mystery. While we can clearly detect these rhythmic flickers, linking a specific frequency to a specific physical process, like the orbit at the innermost stable edge, is incredibly complex. The accretion flow is not a clean, simple disk. It is a turbulent, magnetized, chaotic maelstrom. Multiple types of oscillations can occur simultaneously. There might be radial oscillations where clumps of gas move in and out like a breathing motion. There could be vertical oscillations where the disk itself wobbles like a warped record. Or the entire inner disk might precess, wobbling like a spinning top. All of these processes can produce their own quasi-periodic signals, which then blend together in the X-ray light we receive. It is like trying to identify every individual instrument in a symphony by listening to a single, crowded recording from the back of a concert hall. The signal is there, rich with information, but teasing apart its components is a monumental challenge. The debate continues. Are the dominant QPOS caused by the orbital motion of bright blobs of gas whipping around at near light speed? Or are they the result of instabilities in the magnetic fields threading the disk, which snap and release energy in rhythmic bursts? Each model makes different predictions about how the frequency should change with the black hole's brightness or mass. By observing many different black holes and comparing the QPO signatures to these theoretical predictions, astronomers are slowly deciphering the code. These flickers are more than just curious data points. They are a direct broadcast from the edge of reality, a complex song played by matter in its final, furious dance. Decoding each note could finally tell us if Einstein's vision of gravity holds perfectly true, even in the darkest and most distorted corners of the universe. The complex song of quasi-periodic oscillations is a broadcast from visible matter in its death throes, but an even deeper mystery might be broadcasting from the darkness that surrounds them. Black holes are the ultimate gravitational traps, and that sheer power could make them the universe's perfect dark matter collectors. This leads us to a profoundly speculative yet electrifying idea. What if black holes are not just surrounded by empty space, but by immense invisible halos of dark matter? And what if that dark matter is secretly signaling its presence? We know dark matter exists. Its gravitational pull holds galaxies together and bends light from distant stars, but we have never directly seen a single particle of it. It does not emit, absorb, or reflect light, hence the name. Yet, one leading theory suggests dark matter particles could be their own antiparticles. If that is true, then when two dark matter particles collide under the right conditions, they would annihilate each other in a flash of energy, producing a spray of gamma rays, the most energetic form of light. The key is density. The annihilation rate depends on how densely packed the dark matter is, and nothing packs matter, or in this case, dark matter, more densely than the gravitational well of a black hole. Imagine a black hole, especially a solitary one, drifting through the galactic halo without a companion star to feed on. Over billions of years, its immense gravity would slowly pull in a vast cloud of dark matter particles from the surrounding space. These particles would not fall into the black hole in a neat disk like normal gas. Instead, they would accumulate in a diffuse spherical halo, swarming around the singularity like a dense, invisible hive. In the very heart of this halo, where the density is greatest, the rate of particle collisions would skyrocket. If dark matter annihilates, this region should glow with a faint, distinctive signature of gamma rays. Astronomers have searched for this exact signal. They have pointed gamma-ray telescopes like NASA, Fermi at isolated black holes, and at the supermassive black holes at the centers of dwarf galaxies, environments theoretically rich with dark matter. The goal is to find an unexplained, persistent glow of gamma rays that cannot be accounted for by any normal astrophysical process. No accretion disk, no jets, just a quiet black hole shining with dark light. So far, no unambiguous detection has been made. The signal, if it exists, is incredibly faint, drowned out by the background gamma-ray chatter of the universe. But the search itself is a breathtaking convergence of mysteries. It ties the greatest enigma in cosmology, the true nature of dark matter, to the most extreme objects in gravity's arsenal. A single, clear gamma-ray signal from a quiescent black hole would be a monumental discovery. It would not only reveal the identity of dark matter, but also show that black holes are more than just consumers of light. They would be cosmic beacons, illuminating the invisible architecture of the universe itself through the silent annihilation of ghosts. That search for dark light is a whisper against the thunder of a discovery that shook the world. On September 14, 2015, a signal arrived that was not light, not a particle, but a ripple in the fabric of space itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected a waveform that began with a low hum and rose to a crescendo in a fraction of a second. This was GW150914, the first direct detection of gravitational waves created by the final, frantic orbits of two black holes, one 29 times the mass of our Sun, the other 36, spiraling together and merging. The sound of that merger is often described as a chirp, but that is only the beginning of the story. The true, profound signal came in the aftermath, in the ringdown. Imagine striking a bell. The initial impact creates a loud tone, but then the bell continues to vibrate, humming at its characteristic frequencies as the sound fades away. A black hole is like a bell made of pure space-time. The violent collision of the two merging black holes does not end with silence. It sets the newly formed single black hole ringing. It vibrates, distorting the space around it, emitting gravitational waves as it shakes off the asymmetry of its violent birth and settles into a smooth, final shape. This fading hum is the ring down. It is an exponentially decaying signal, a fingerprint written in the language of gravity. According to Einstein's theory, a black hole in its final, stable state is described by just three numbers: its mass, its electric charge, which is negligible, and its spin. This is the famous no-hair theorem, meaning a black hole has no other distinguishing features, no hair. The frequencies and decay rates of the ring-down vibrations are determined solely by the mass and spin of this final black hole. By meticulously analyzing the ring-down signal from GW 150914, scientists could essentially weigh and measure the spin of the newborn 55 solar mass black hole. The data matched the predictions of general relativity with stunning accuracy. It was a direct test of the no-hair theorem, a confirmation that the final object behaved exactly as a pure, smooth black hole should. The mystery lies in the incredible challenge of extracting this faint, fleeting signal from the data. The ring down is buried in the final moments of the catastrophic chirp, and it fades so quickly it is almost lost in the detector's own noise. It is like trying to hear the last, soft echo of a gong after it has been struck with a sledgehammer. Advanced data analysis techniques comparing the signal to millions of theoretical templates were required to tease it out. This is why future detectors, like the planned Laser Interferometer Space Antenna, or LISA, are so revolutionary. With their vastly improved sensitivity, they will hear the ring down with crystal clarity. We will not just confirm the no-hair theorem, we will test it with precision, listening for any tiny deviation in the ringing, any unexpected frequency, any hint that the vibrations last a fraction longer or shorter than predicted would be a bombshell. It could mean the final object is not a perfect black hole as we understand it. Perhaps it is a more exotic object like a boson star or a gravistar, leaving a subtle imprint in its final vibrations. Or it could reveal new physics about the very nature of space-time at the event horizon. The ring down is the death knell of a black hole merger, and in its fading tone, we hear the purest signal of gravity's ultimate power, a direct line to the moment when two monsters become one, and the universe itself trembles before settling back into a silent, dark equilibrium. The ring down's pure tone is a vibration of clean space-time, but the environment around a feeding supermassive black hole is anything but clean. It is a factory of cosmic dust and exotic chemistry, glowing with a warmth we can feel across the universe. When we point infrared telescopes at the hearts of active galaxies, we see a brilliant, unmistakable signature, a torus of dust and gas swirling around the central engine. This dusty donut absorbs the fierce X-rays and ultraviolet light from the accretion disk and re-radiates it as infrared heat. Yet, buried within that familiar glow are spectral fingerprints that do not belong. Specific wavelengths of infrared light shine brighter than any known type of cosmic dust should allow. This is an unidentified infrared emission, a persistent whisper from the inner sanctum that hints at materials we are only beginning to understand. One of the most compelling suspects is not a common silicate or carbon grain, but something far more precious: nanodiamonds. Picture the extreme conditions in that dusty torus, a region bathed in brutal radiation and shockwaves from the black hole's activity. Under that tremendous pressure and heat, clusters of carbon atoms could be forced into the rigid, crystalline structure of diamonds, but on a scale smaller than a virus. These nanoscale gems would have a unique property. They vibrate at specific frequencies when struck by infrared light, emitting their own characteristic glow. Finding their signature in the galactic core would mean that black holes are not just destroyers, they are jewelers, forging the hardest known natural substance in their violent workshops. But nanodiamonds are not the only candidate. Other exotic forms of carbon, like tiny flakes of graphene or mysterious molecules called polycyclic aromatic hydrocarbons, could also be responsible. These complex compounds are the building blocks of soot, and finding them near a black hole suggests a surprising possibility that the same basic organic chemistry that leads to life on planets might also be sparked in the most hostile places imaginable. The central mystery remains: what process creates and sustains these materials so close to the inferno? The radiation near a supermassive black hole is powerful enough to blast ordinary dust grains apart, vaporizing them into their constituent atoms. For any solid structure to survive, let alone form, it must either be incredibly resilient or be constantly replenished by some rapid, unseen factory. Perhaps shock waves from jets or collisions within the torus provide momentary pockets of extreme pressure, a cosmic anvil that forges diamonds in an instant before they are swept away. Or maybe we are seeing the signature of a completely unknown physical process, where the intense radiation fields themselves catalyze the growth of exotic carbon networks in ways our laboratories cannot yet replicate. This unexplained infrared glow is more than a spectral curiosity. It is a clue to the secret life of galaxies. It tells us that the chaos around a black hole is not random destruction. It is a crucible for complex chemistry, creating materials we are only now learning to see. Each unidentified wavelength is a question, asking what else is being forged in the dark heart of a galaxy, waiting to be scattered into the cosmos. The unexplained infrared glow from galactic cores speaks of chemistry forged in chaos, but our own galaxy holds a different kind of spectral ghost, one that paints the sky in microwaves. While the colossal Fermi Bubbles stand as monuments to gamma rays, a subtler signal fills the same vast space between them. Satellites like WMAP and Planck, mapping the cosmic microwave background, detected a faint, diffuse haze of microwave emission precisely coinciding with the interior of those gigantic gamma-ray orbs. This is not the afterglow of the Big Bang. It is something local, something emanating from our galaxy's heart, and its origin is a heated debate among astrophysicists. One compelling explanation directly ties it to the same ancient cataclysm that created the Fermi Bubbles. If that event was a sustained eruption from Sagittarius, a star, it would have blasted out not just gas, but a storm of high-energy electrons. These electrons, spiraling at near-light speed through the Milky Way's magnetic fields, would produce a specific type of radiation called synchrotron emission. This same process creates the gamma rays at the bubble edges, where the shockwave is most intense. The microwave haze, then, could be the softer, lower-energy echo of those same electrons, filling the entire volume of the bubbles like a lingering fog. It would be the dying whisper of particles that have been traveling for millions of years, slowly losing their energy but still painting the interior of these structures with a faint radio glow. This elegant idea neatly ties two unexplained signals together into a single, epic story of our black hole's violent past. However, a challenger theory complicates the picture. This haze might not come from electrons at all, but from something astonishingly mundane: dust. Not just any dust, but ultra-tiny, spinning nanoparticles. Imagine a grain of interstellar dust smaller than a virus, made of carbon or silicate. When it is struck by a single ultraviolet photon from a star, it can begin to spin, tumbling wildly at incredible speeds. This rapid rotation causes it to emit radiation, and for the smallest grains, that radiation falls right into the microwave band of the spectrum. Could the haze simply be the collective hum of trillions upon trillions of these spinning nanodust grains, concentrated in the galactic center? The debate is crucial because each origin tells a different story about the energy and aftermath of the explosion. If the haze is synchrotron radiation, it confirms that the Fermi Bubbles event filled our galactic center with a long-lasting sea of relativistic particles, a cosmic accelerator whose effects are still felt today. It means the explosion's energy was channeled powerfully into particle acceleration. If the haze is spinning dust, it suggests a different legacy. It would mean the eruption also created or distributed vast amounts of fine particulate matter, seeding the galactic center with the raw materials for future chemistry and perhaps even future planets. Unraveling this microwave signal is the key to understanding the full spectrum of that ancient violence, from the highest energy gamma rays to the softest radio whispers, building a complete picture of how a sleeping giant once awoke and reshaped its home. The soft microwave haze from our galactic center is a lingering echo of ancient fury, but some black holes announce their violence with a startling two-part act. A star wanders too close, is shredded into a streamer of gas, and the black hole feasts. Astronomers see the brilliant flare of light as that stellar material heats up, a classic tidal disruption event. Yet for a rare few, the story does not end there. Months after the initial cataclysm, when the visible light flare has begun to fade, a new and far more powerful signal erupts, a relativistic jet, a beam of plasma and radiation launched at nearly the speed of light. This delayed outburst forces us to rewrite the timeline of destruction. The event known as at 2022 CMC is the perfect example. In February of 2022, optical telescopes caught the initial flash of a star being torn apart. But the real shock came from the world's most sensitive radio observatories. Roughly 2 months after the first flare, they detected an incredibly bright and rapidly brightening source of radio waves. This was the signature of a jet, but one that had taken its time to appear. The delay presents a fundamental puzzle. If the jet is powered by the black hole's accretion of the stellar debris, why did it wait? One leading theory is one of assembly. When the star is first shredded, the gas is chaotic, a messy rain of material falling in from all directions. It takes time, perhaps weeks or months, for this chaos to settle into a stable, rotating accretion disk, the organized, swirling whirlpool needed to power a jet. Furthermore, that disk must become magnetically launch-ready. The intense magnetic fields threading the disk need to be twisted and amplified to the point where they can act like a cosmic railgun, channeling and accelerating material away from the poles. The 2-month delay at 2022 CMC could simply be the construction and charging time for this extreme engine. Another possibility is one of perspective. The jet might have launched almost immediately but been initially hidden from our view. In the early, dense fog of stellar debris, the jet could have been smothered, its light absorbed and scattered by the surrounding cloud of gas. Only as that cloud expanded and thinned out months later did the brilliant beam finally punch through, revealing itself to our telescopes. This scenario is like a lighthouse shrouded by a thick, rolling fog. The beacon is on, but we cannot see it until the weather clears. At 2022, CMC was exceptionally bright because the jet was pointed almost directly at Earth, making its delayed reveal all the more dramatic. These delayed jets challenge the very notion of cause and effect around a black hole. They tell us that the process of turning a star into a cosmic particle beam is not instantaneous. It is a staged drama with an intermission between the initial act of destruction and the final, focused blast of creation, forcing us to reconsider how long it takes for a singularity to organize its fury. The delayed jet at 2022 CMC was a time-lapse portrait of fury, but in April of 2019, humanity received a snapshot of a black hole's true face. For the first time, we saw the shadow of a monster. The Event Horizon Telescope collaboration unveiled the image of the supermassive black hole at the heart of Galaxy Messier 87, a cosmic titan weighing in at 6.5 billion times the mass of our Sun. This was not a photograph of the black hole itself, which is impossible, but of its silhouette against the brilliant glow of its superheated accretion disk. The dark central shadow, surrounded by a fiery ring of light, became an instant icon. Yet for all its clarity, the image held a striking and deliberate puzzle. The ring of light is not symmetrical. One side, particularly the bottom portion in the image, shines with a fierce, brilliant intensity, while the opposite side appears noticeably dimmer and more diffused. This is not an error or a trick of the camera. This asymmetry is the signal, a direct message written in the physics of matter moving at the absolute edge of reality. The explanation lies in a phenomenon called relativistic beaming, a consequence of material orbiting at nearly the speed of light. Imagine the accretion disk as a furious whirlpool of plasma. The side of the disk where material is spinning toward us is in effect chasing the very light it emits. This motion compresses the light waves, boosting their energy and making that side of the ring appear dramatically brighter. Conversely, the side where material is moving away from us stretches the light waves, red shifting and dimming them. This creates the lopsided halo we see. The bright crescent is essentially a cosmic headlight pointed in our direction by the black hole's immense gravity. But this simple explanation opens a far more complex investigation. The precise pattern of that brightness holds the key to decoding the black hole's spin, the detailed structure of its magnetic fields, and the exact behavior of the accretion flow. Is the disk a thin, orderly sheet or a thick, puffy torus? Is the material flowing in a smooth river or in chaotic, magnetized clumps? The asymmetry in the ring is our only visual clue. By comparing the image to millions of supercomputer simulations that test different models of physics, scientists are performing a form of cosmic forensics. They found that the observed brightness pattern strongly suggests the black hole is spinning, and that its spin axis is tilted relative to our line of sight, pointing its relativistic headlight somewhat in our direction. Furthermore, the subtle gradients in the ring's light hint at the powerful magnetic fields that thread the disk, fields that are essential for launching the galaxy-spanning jet we see erupting from M87. Every pixel in that historic image is a data point, a measurement of how gravity bends light and motion warps perception at the most extreme scale imaginable. The dark shadow is the silence of the event horizon, but the bright, uneven ring is its loudest signal, a luminous fingerprint of the chaotic dance happening just microseconds before a total and final vanishing. The fiery, lopsided ring of M87 is a signature of matter orbiting at the brink, but some cosmic engines shine with a brilliance that defies all known limits. Scattered near the edges of galaxies, often far from the central supermassive black hole, astronomers find objects that outshine entire star clusters in one specific way. They are ultra-luminous X-ray sources, or ULXs, and their signal is a torrent of X-rays so intense it should not be possible. A typical stellar mass black hole, formed from a collapsed star, has a theoretical maximum brightness called the Eddington limit. This is the point where the outward pressure of radiation from the infalling matter perfectly balances the inward pull of gravity. Push past this limit, and the radiation should blow away the surrounding gas, shutting off the fuel supply and dimming the object. It is a universal throttle, yet ULXs blast out X-rays at 10, 100, sometimes even 1,000 times this calculated limit. It is as if a single candle suddenly began shining with the ferocity of a lighthouse beacon. How do they cheat this fundamental law of physics? One possibility is that we are witnessing stellar mass black holes in a state of extreme, messy gluttony. They might be accreting material not in a neat, thin disk, but in a thick, puffy, supercritical flow. Imagine trying to drink from a fire hose. The water comes in faster than you can possibly swallow, and it sprays everywhere. In this chaotic model, material falls onto the black hole from all directions in a dense, spherical cloud. The intense X-rays produced deep within this shroud struggle to escape, bouncing around and losing energy before finally emerging. This process could allow the black hole to appear brighter in X-rays than the simple Eddington limit predicts, because the radiation is not pushing directly outward against the infall. It is a loophole in the physics of gluttony, but there is another, even more tantalizing explanation. perhaps these are not stellar mass black holes at all. They could be the long-sought missing link in the cosmic hierarchy, intermediate mass black holes. These would be monsters with masses ranging from a few hundred to a few 100,000 times that of our Sun, bridging the gap between the stellar corpses we see and the supermassive giants at galactic centers. An intermediate mass black hole accreting at a normal, steady rate could easily produce the staggering X-ray luminosity of a ULX without breaking any rules. Its higher mass means a higher Eddington limit, so its brilliance is not a violation, but a signature of its true, hidden size. Finding one would solve a major puzzle in cosmology, explaining how the supermassive black holes in the early universe grew so big so fast. They needed seeds, and intermediate mass black holes are the perfect candidates. The extreme X-ray signal of a ULX, therefore, is a cosmic identity crisis. Is it a relatively small object breaking the rules of consumption, or a much larger one hiding in plain sight? Each brilliant point of light is a question mark, challenging our understanding of how black holes feed, grow, and ultimately shape the galaxies they inhabit. The brilliant, rule-breaking glare of an ultra-luminous X-ray source is a solitary beacon. But if you could listen to the universe with ears tuned to space-time itself, you would hear a chorus. Beneath the loud, distinct chirps of individual black hole mergers, there is a permanent, underlying hum. This is the gravitational wave background, a cosmic murmur built from the overlapping ripples of every supermassive black hole binary that has ever spiraled together across billions of years of cosmic history. It is not a single signal, but a collective roar, a stochastic ocean of whispers where no single wave can be distinguished. For decades, this was a theoretical prediction. Then, in 2023, multiple international collaborations using pulsar timing arrays announced they had heard it. Their method is a masterpiece of cosmic precision. They monitor the steady, metronomic flashes from dozens of millisecond pulsars scattered across our galaxy. These pulsars are nature's most perfect clocks. As a gravitational wave, a ripple in space-time, passes between Earth and one of these pulsars, it minutely stretches and compresses the distance, causing the arrival time of the pulses to speed up or slow down by mere billionths of a second. By tracking an entire array of these pulsars over 15 years, scientists detected a correlated pattern in their timing, a telltale sign that a common force was affecting them all, the gentle squeeze and pull of the gravitational wave background. The hum is real, but its volume is the mystery. The amplitude of this murmur, how loud it is, holds the key to its origin. Does it match the expected cacophony from the known population of supermassive black hole binaries, the giant pairs that form when galaxies merge? If so, it beautifully confirms our standard model of cosmic structure. Yet, early hints suggest the hum might be louder than expected. A more powerful signal would point to something beyond the ordinary choir. It could be the voice of exotic physics from the universe's first moments. One tantalizing possibility involves cosmic strings, hypothetical, infinitely thin defects in the fabric of space-time left over from the Big Bang. If they exist, these vibrating strings could snap or form loops, releasing titanic bursts of gravitational waves that would contribute to the background hum. Another source could be violent phase transitions in the early universe, moments when the fundamental forces of nature suddenly changed, sending shockwaves through the cosmos that would still be ringing today. Both of these exotic phenomena are also leading candidates for creating primordial black holes. A louder than expected murmur could therefore be the indirect signal of a hidden population of these ancient black holes, their mergers contributing a fierce additional layer to the cosmic noise. We are now listening to the universe's deepest baseline, a frequency that holds the integrated history of its most massive collisions. Deciphering whether this hum is the sound of expected giants or the echo of primordial ghosts will rewrite the story of how our cosmos evolved from a silent singularity into a symphony of structure. That cosmic hum is the sound of giants merging in the dark, but in our own galactic neighborhood, the loudest signal is often a profound silence. Drifting through the Milky Way are binary systems that present us with a direct and unsettling contradiction. We see a star, a perfectly normal sun, tracing a graceful ellipse through space. Its motion reveals the unmistakable gravitational tug of an unseen companion, an object with several times the mass of our own sun. By all rights, that much mass compressed into such a small volume should be a brilliant beacon, a pulsar, a bright X-ray source, something. Yet when we point our telescopes at that precise point in space, we see nothing at all. No light, no radio pulses, no X-ray flicker, just empty space where a monster should be. These are the empty black hole binaries, and their primary signal is the absence of one. Systems like Gaia BH1 and Gaia BH2, discovered by the European Space Agency's Gaia mission, are textbook examples. In Gaia BH1, a sun-like star orbits an invisible point every 185 days. The math is inescapable. The unseen companion weighs about 10 solar masses. That is far too heavy to be a neutron star, which collapses under its own weight above roughly 3 solar masses. The only object that can contain that much gravity in such darkness is a black hole. Yet this black hole is not just dark, it is dormant. It possesses no glowing accretion disk, no hungry swirl of superheated gas. It is a cosmic predator that has, for now, stopped hunting. This quietude is the central mystery. Why are these black holes so utterly dark? In a typical X-ray binary, the black hole actively strips material from its companion star, creating that luminous, energetic disk we can easily detect. But in these empty binaries, the dance is different. The companion star is often a main sequence star like our Sun, holding onto its atmosphere tightly, or it orbits at a respectful, safe distance. The black hole is not being fed a steady stream of gas. It is dining on the thin, sparse wind that the star emits, a meager sustenance that fails to ignite the brilliant engine of an accretion disk. It is a starvation diet, resulting in a black hole that emits virtually no light of its own. The discovery of these silent giants challenges our models of how binary star systems evolve. Conventional theory suggested that the violent supernova explosion that creates a black hole would often disrupt the binary, kicking the system apart or at least altering its orbit dramatically. Finding such seemingly peaceful pairings with a normal star quietly orbiting a massive black hole implies that some black holes can be born with a gentle nudge rather than a catastrophic kick, leaving their stellar partners undisturbed. This forces astronomers to revise the story of stellar death and binary survival. Most importantly, each empty binary we find is likely just the tip of an iceberg. For every one we detect by the subtle wobble of its companion star, there may be hundreds or thousands more lurking unseen in the galactic dark. They represent a vast, hidden population of dormant black holes, cosmic ghosts drifting silently through the Milky Way. They are the universe's sleeper agents, quiet now, but possessing the terrifying potential to awaken. If their orbital dance changes, or if the companion star evolves and expands, that trickle of stellar wind could become a flood. The silent predator could suddenly switch on its accretion disk and transform into a brilliant, violent X-ray source, announcing its presence with a shout after eons of silence. Their discovery tells us that the galaxy is not just dotted with the brilliant beacons of active black holes, but saturated with sleeping ones, waiting in the dark for a change in the cosmic weather. That profound silence in our own galaxy echoes a much smaller, but no less puzzling, quiet from our own cosmic backyard. Decades ago, as the Pioneer 10 and 11 spacecraft hurtled toward the edge of our solar system, engineers noticed something was off. Their trajectories were ever so slightly wrong. An unknown force, incredibly faint but persistent, was tugging on them, creating a tiny, unexplained deceleration back toward the sun. This was the Pioneer anomaly, a drift measured in mere nanometers per second squared, a whisper of a push against humanity's first interstellar messengers. After years of meticulous analysis, the most widely accepted explanation turned out to be remarkably mundane: the gentle but constant pressure of heat. The spacecraft's radioactive power sources emitted warmth, and photons carrying that heat radiated unevenly from the probe's bodies. This anisotropic thermal radiation acted like a faint, braking rocket, slowly nudging the Pioneers off their predicted path. Case closed for most, yet for a time the anomaly fueled wilder speculations. Could it be the gravitational fingerprint of something massive and unseen lurking in the frozen darkness beyond Pluto? This fringe idea never gained mainstream traction, but it connects a local navigational quirk to the grandest of cosmic mysteries. Today, that same line of questioning has resurfaced with a different target. Astronomers tracking the orbits of distant icy objects in the Kuiper belt have found their paths are curiously clustered, as if shepherded by an invisible hand. The leading hypothesis to explain this orbital oddity is a hypothetical planet 9, a world perhaps 5 to 10 times the mass of Earth, orbiting far beyond Neptune. But another, far more exotic possibility exists. What if the shepherd is not a planet at all? What if it is a primordial black hole, a captured relic from the Big Bang, no larger than a grapefruit but containing several Earth masses, could exert the same gravitational pull on those distant ice worlds? It would be a dark, freezing specter, emitting no light, detectable only by the subtle wobbles it imposes on everything around it. This idea transforms the search for a new planet into a hunt for something infinitely stranger. The speculative leap from the Pioneer anomaly to a hidden black hole in our solar system is vast, but it underscores a thrilling truth. The same gravitational whispers we use to find black holes in distant galaxies, the same tiny perturbations in motion, could be signaling a monster in our own celestial basement. It reminds us that unexplained signals come in all scales, from the faint drift of a human-made probe to the twisted orbits of ancient ice dwarfs. Each anomaly, no matter how small, is a question. And sometimes the answer to a local mystery might not be a new world, but a door to a darker, more profound understanding of the universe itself. From drifting spacecraft to silent binary giants, the universe speaks in a language of whispers and roars. We have traveled from the solitary cry of the wow signal to the cosmic hum of merging supermassive black holes, encountering 25 distinct enigmas along the way. Each one is a different dialect in the grammar of gravity and chaos. We have seen gravitational waves ring space-time like a bell, ghostly neutrinos point directly to particle cannons in distant jets, and colossal radio circles hang in the dark like fossils of ancient fury. We have listened to the steady heartbeat of a feeding black hole and the chaotic stutter of a repeating fast radio burst. We have witnessed the brilliant, rule-breaking glare of ultra-luminous X-ray sources and the profound, telling silence of dormant black holes orbiting sun-like stars. This is not a catalogue of dead ends. Every single unexplained signal is a beacon. It is a flickering guidepost pointing toward physics we have not yet written, toward truths that lie just beyond the edge of our current equations. These mysteries collectively reveal a fundamental truth: that black holes are not the simple, silent monsters of old textbooks. They are complex cosmic engines, transformers of matter and energy on a scale we struggle to comprehend. They are broadcast towers, particle accelerators, gravitational lenses, and chemical forges. Their full language, a symphony composed of light, gravity, particles, and silence, is one we are just beginning to decipher. So now, the question turns to you. Which of these 25 signals captured your imagination the most? Was it the rhythmic mystery of the black hole heartbeat, GRS 1915 plus 105, or the cosmic scale ghost story of the odd radio circles? Do you think the solution to dark matter might be hiding in the gamma ray glow around a quiet singularity? Share your thoughts and theories in the comments below. Your perspective is part of this ongoing investigation. If you want to join us for more deep dives into the universe's greatest puzzles, be sure to like this video and subscribe. The conversation about what lies in the dark is only just beginning.